So chapter 4, we finally get to talk about atoms and elements. And then the first thing we're going to talk about, basically how everything is made of atoms. I've already said this, but everything's made of atoms. They're the building blocks of everything. They're the reason that you can see, well, yeah, I mean, the reason you can see things, the reason you can hear things, taste, smell things. The atom is the smallest identifiable unit of an element. So all of the elements that are on the periodic table are individual atoms, just different types of atoms, different flavors. There are about 91 different kinds of atoms. If you go and look at a periodic table, there are more on there than that. But there's a whole set of elements that are man-made by colliding really heavy elements together. And they last for like nanoseconds. So they're gone pretty much as soon as they're created. So there's gonna be a lot of concepts here at the beginning, and I'll try to highlight the things that are the most important. So atom is the smallest identifiable unit of an element. Atoms are incredibly small. It's really, 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 really hard to conceptualize how small they are. Like if you looked under a microscope, you need a very, very special scanning tunneling microscope or scanning electron microscope, or sorry, scanning electron or tunneling electron microscope to be able to see a single atom. Because if you were to take a pebble and then blow up all of the atoms inside of that pebble to the size of the pebble, that would make that pebble the size of Mount Everest, the tallest mountain on Earth. It would be larger than Mount Everest. The idea of the atom, which I think I hinted at in the first week, was discovered by these two, I believe, Greek dudes who were sitting around and were bored. Democritus in particular is credited with sitting and thinking, if I could cut things in half, at what point would I stop being able to cut it in half? All right, so if you took this calculator, cut it in half, cut it in half, cut it in half. His theory then was that there would be some piece, some teeny tiny piece that you could not cut in half. If you actually had 12 grams of carbon, I did the math, you could cut it in half 79 times and you would have one atom of carbon left. But atomos, or atoms, comes from atomos, meaning indivisible. So sort of at the root of what they are. So this idea, though, was really just a theory up until John Dalton's atomic theory, where he proposed that each element is composed of tiny indestructible particles called atoms, that all atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements, and that atoms combine in simple whole number ratios to form compounds. So here's the scanning tunneling microscope. I guess I was mixing up both of those names. But at IBM, they did this. I wish this had a date on it. I don't remember when this was. So they moved xenon atoms around until it spelled IBM. They look like little cones here. But that's a peculiarity of the method for looking at them. They're actually, well, in general, more spherical in shape. Teeny tiny spheres, submicroscopic. So one of the first theories of the atom was developed by J.J. Thomson when he discovered a smaller particle called the electron. So the electron is negatively charged, smaller and lighter than atoms, than whole atoms, and they're uniformly present in many different kinds of substances. This is how in metals especially, the electrons are pretty free to move around, and that's why they conduct electricity. So his model was the plum pudding model, where he proposed that the electrons were held in a sphere of positive charge in every atom. I know you hear pudding, you think of like chocolate pudding or vanilla pudding, like goop. That's not what plum pudding is. It's more like fruitcake. So you imagine a fruitcake, the electrons are the little pieces of fruit suspended throughout the cake. He ended up being wrong, but this was one of the first ideas, separating the atoms into individual parts. So his theory was disproven by Ernest Rutherford. He set up this, what I think is a very cool experiment. He had this source that's firing alpha particles at a very thin sheet of gold. His theory was that if the plum pudding model is correct, and it's just this sort of glob, this cake of positive charge with electrons throughout it, you could fire these alpha particles through it, no problem. They shouldn't deflect. They should pass right through. For the most part, they went through, but some of them were deflected, and some of them were deflected really far back towards the detector, at these sharp angles. And I do want you to know about this. Oops. And positively charged with alpha particles fired at a thin sheet of gold. A few were deflected. So this is important because if the plum pudding model is correct, they should just pass right through with very, very minimal deflection. The opposite was true though, and some of them were deflected. And it says, this is a quote. He said, "This is about as credible as if you had fired a 15-inch shell at a piece of tissue paper and had the shell come back and hit you in the face." I guess I added that hit you in the face, right? So if you were shooting a gun at a fruitcake and those bullets bounced back at you, is about how credible this was at the time. So because of this, though, they were able to really discredit his theory and say, that's wrong. We need to come up with a new theory for what the atom is actually like. So then we got the nuclear theory of the atom. You should know these ones. So most of the atom's mass and all of its positive charge are actually contained at the center of the atom, in the nucleus. Most of the volume of the atom is actually empty space. Actually, it's so much empty space inside of each atom that if there was no repulsion between atoms, you could just pass through anything. And then the electrons are dispersed around in that empty space. And the third important thing is that the number of negatively charged electrons outside the nucleus is equal to the number of positively charged particles, which are called protons, inside the nucleus. So the atom is electrically neutral. Just for base elements, they're electrically neutral. Which I should go back and clarify too a little bit. So for that quiz where you need to memorize the charges, the elements on this periodic table, is there a way to make this full screen? As they are on the periodic table, are neutral. When I say that group 1 has a positive charge, positive 1 charge, those are the charges that they form. Well, it's the only charge that they do form. But on the periodic table, they're all neutral. We'll get into that more though. Oops, this way. Right. So as more research was done on this, as science developed, we were able to take better and better looks and better guesses at what the structure of the atom actually was. And so we discovered that there are positively charged particles called protons. Oops. Positively charged protons and neutral particles called neutrons inside the nucleus. And the nucleus makes up more than 99% of the mass of the atoms, or the mass of atoms, but only occupies a very small fraction of its volume. And then those electrons are distributed through a larger region that don't have much mass. It's kind of like a cloud of fog, electrical fog around the nucleus. Protons and neutrons have similar masses. We have them right here on this table. So their mass in grams or kilograms, 1.6 times 10 to the negative 27. Pretty much the same for both of them. And then an electron has even less mass than that. To more easily talk about protons and neutrons and the masses of atoms and molecules, we devised a unit called the atomic mass unit, which is 1/12 the mass of a carbon atom with 6 protons and 6 neutrons. So that a proton is right about 1 AMU, a neutron is 1 AMU, and then electrons, which we don't talk about the mass of electrons very often, still at 0.0005 AMU. But this is a lot easier to use than these times 10 to the negative 27 numbers. So you should definitely know on this, proton, neutron, electron, that the masses of these, relatively the masses of those, and then that the charges are +1 for a proton, 0 for a neutron, and -1 for an electron. So if a proton had the mass of a baseball, an electron would have the mass of a grain of rice. That's how different the masses are between those. So it's about 2,000 times as massive as that electron. There's actually a grain of rice there. So one of the weird things is that we see matter as solid because of the scale that we exist at. But most of it is empty space. And so if you're to zoom in far enough with a scanning tunneling microscope, you could see this empty space in solid matter. Okay, so electrical charge is super important for how we talk about and understand the behavior of atoms. You know, why does sodium chloride, right? Sodium chloride's table salt. Why do those bond together to form table salt? Why don't they just stay as their individual elements? So it's going to be really important to understand these fundamentals about electrical charge. So opposite charges attract each other. Highlight that better. Like charges repel each other. So if you have a proton and a proton, they should repel each other. In the nucleus of an atom, they're actually held together by a weird quantum force that we call the strong force. I feel like physicists at one point just kind of got lazy with naming things. So there's the strong force and the weak force. And then positive and negative charges cancel each other out so that a proton and electron, when paired, are charged neutral. So you can use positive charges to cancel out negative charges. And most of the time, we're moving negative charges around. So for the elements on the periodic table, just because I have this periodic table here, they are all, there's got to be a way to close this, right? They are all identified by, I don't have a pointer for this. Oh, let's do that. So copy. Sure. Okay. So these can all be identified by the number of protons that they have. So we look at a periodic table, and this is 1, then we go over here, we have 2, and then for those go away, 3 and 4, and so on and so forth. That number is the number of protons that each of those elements has. And the number of protons identifies it as that element. You can't have beryllium with 3 protons because that's would be lithium. So we call that atomic number Z, which I know, why isn't it A? So the atomic number is Z. So each element has a unique number of protons. Oh, there's a periodic table right there. I always forget what's coming up next. So in each of these, in any periodic table, you'll have the atomic number, which is Z. You'll have the chemical symbol, which you need to memorize for next week, and the names. And we'll cover atomic masses here in a little bit. So element symbols are a very convenient shortcut for writing out different chemicals, or for elements, the chemical symbols for elements. And they're 1 or 2 letter abbreviations. Most of them are based on the English names, but some of them are not. And those are usually the harder ones to memorize. If it helps, they have, those ones are based on their historical names. So potassium, I mean, is based on Kalium, which is why it's K. Sodium is based on natrium, which is why it's Na. You can go through that list. Yeah. The element of surprise. All right, so without having a periodic table on hand, what is this first element? Sodium. Yep, sodium. And then the atomic number for each element. I actually don't know what it is for sodium. You come over here. So sodium is 11. It's on the left side here. Oops. Sodium. So the atomic number Z equals 11. Nickel. I know I heard some people already saying it. Nickel is, so it's like 28. So this is one of the reasons too that I have you at least memorize the names, because there's a lot of elements here and it can be hard to find things. Z 28. P. It's not potassium. Phosphorus. I feel like I should know phosphorus. Phosphorus is over here, it's 15. Oops. Ta. Ta-da. Actually, I don't even know what Ta is. I think it's tantalum. 73. Yeah, tantalum. As blurry as that is. So 73. If you're struggling to memorize the periodic table of the elements, I'm not requiring you to remember all of them, just 1/3, roughly 35. Daniel Radcliffe does on some interview at one point. He did all of the elements. There's like a song that he has memorized. So, oh yeah, this is actually a really cool thing about the periodic table. When you organize it like it is, And Dmitry Mendeleev came up with this. He proposed the periodic law, so that if you arrange the elements in order of increasing relative mass, or atomic mass in this case, or atomic number, certain sets of properties recur periodically. So the exceptions are hydrogen and helium. Well, not exceptions really, but you go 1 and then 2, and then each row has 8 sort of in the set, not including the transition metals. So right, 1, 2, 3, 4, 5, 6, 7, 8. And when you arrange them in this way, this is why, this is one of the periodic law sort of patterns, is that hydrogen, lithium, sodium, potassium all form +1 charges as their predominant charge. Beryllium, magnesium, calcium all form +2 charges as their most common charge. So these elements are all very similar, and actually there's some cool sci-fi stuff out there where, you might know, all life on Earth is based on carbon, right? That makes up most things. Carbon is able to form a lot of different unique structures, but silicon has a lot of the same properties as carbon. So what if there's a planet out there that has life based on silicon instead? Because it can do a lot of the same things. So patterns in the periodic table. There are some other patterns, important patterns that we'll talk about. One of them here is that the difference between metals, nonmetals, and metalloids. Metalloids are weird and have some properties of metals, some properties of nonmetals. So these are all the metals. It's supposed to ask you, most of the elements on the periodic table, or it would be a statement, like most of the periodic table elements on the periodic table are metals. That would be true. Vast majority are metals, because the only nonmetals are hydrogen over here, and then all of these green ones. And then there's just a few metalloids. So we have metals occupying the left side of the periodic table. They are good conductors, so both heat and electricity. They're malleable. You can pound them into flat sheets. And they are ductile, so you can draw them into wires. If you stretch a metal to pull on both ends of a metal, it will pull into wires if it doesn't break first. They're also often shiny. When they're clean, when it's the pure element metal, right? We talked about, iron can rust, and that's not shiny. But the elemental metals are shiny. And they also tend to lose electrons when they undergo chemical changes. So some examples being iron, magnesium, chromium, sodium. Yeah. So when they lose electrons, it also means that they form positive charges. So the metals pretty much all just form positive charges. So the nonmetals, so we had at the top right side of the periodic table, have pretty much the opposite properties. We have some that are solids at room temperature. Pretty much all the metals are solids, mercury being the one liquid. There are some, a bunch of the nonmetals are gases, but they tend to be, in general, poor conductors of heat and electricity. And they also tend to gain electrons when they undergo chemical changes. So they form negative charges. Examples of nonmetals being oxygen, nitrogen, chlorine, and iodine. Carbon is also a nonmetal, an example of a solid nonmetal, whereas these are all, no, not all gases. Oxygen, nitrogen, chlorine, predominantly gases. Iodine can be solid. or is a solid generally. Metalloids really do just have some properties of metals, some properties of nonmetals. They're also called semi-metals. They have mixed properties. They're most important for things like silicon, which is a semiconductor. So they have intermediate electrical conductivity. And I mean, that's what makes all of the computer chips go. They're all made on silicon using the property of when you pass a charge across silicon, when you force enough voltage across silicon, it becomes electrically conductive, like in all directions. So use those as micro switches. I'll put a picture in there. Okay, so I classify each of these as a non-metal, or metal, non-metal, or metalloid. I mean, if you're playing your odds, go with metal, but you could also look at a periodic table if you have one. If you have your book, it's in there. But I'll pull the periodic table up again. So we got sulfur. So where is sulfur? Oh wait, I can put the, I can do this again. That's not big enough to see. Is that big enough to read it all? I can kind of barely read it from here. Okay, so sulfur is here. So is it a metal or non-metal? Don't look at this. Yeah, it's a non-metal. How about chlorine? Also a non-metal, right next to sulfur. TI, not Texas Instruments. Where is it on the periodic table? Actually, it should be 81. No, that looks like titanium. It's titanium, by the way. Oh, 22. Oh yeah, it is way up there. Titanium is one of my favorite metals. It's a metal. It's like the highest strength to weight ratio. So it's very light metal, but also very strong. Use it to make the SR-51 Blackbird, which that's a cool plane because it went so fast that the hull heated up so much that they had to leave giant gaps in it, because as it was flying, the metal would expand because the whole thing was made of titanium. It would expand and then close those gaps. So before it took off, it leaked a lot of fuel in preparation for those gaps closing from the thermal expansion. Okay, SB, antimony. Yep, antimony. So, sorry, the question was, is it a metal, non-metal, or metalloid? Metalloid. Two L's, right? Yeah, metalloid. So this is one where you can memorize the trend, broad trend. If it helps to, starting with this zigzag line, you start there with boron and then go across and down and across and down and across and down. Those elements along that line are the metalloids. Then to the right of those is non-metals, and to the left are metals. So we do break this up into main group elements, which are groups 1 and 2 here. And then this can be a little bit confusing, but it doesn't have to be. So if we were doing just all of the groups across, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like 7. Oh no, 8 is 3 of them. 9, 10, or sorry, 7, 8, 9, 10, 11, 12, 13, right? 14, 15. And that's how these are labeled on the table in your book, right? As 1, 2, 3, 4, 5, 6, 7. They also have the main group separate labels. So 17, 16, and 17 are the same as 6A and 7A. Like 13 is 3A. For the most part, we will be looking at main group metals. You'll have to know some transition metals, and those are on the list. But for the most part, we'll be working with the main group elements. We also have some special names for some of these groups. So on the left, we have the alkali metals and the alkaline earth metals. Then this entire block inside of here are the transition metals. These guys don't have names. Then the halogens and the noble gases. And then as a bonus, 6A are also the chalcogens. And then the lanthanides and actinides, which are usually pulled out because they actually split the periodic table here. So these 14 elements across, there's 28 elements in total, but to make this periodic table just super long. So we usually split them out. We'll talk more about why they're doing these groups in a later chapter. So these are, though, they have special names because they have patterns in their properties. So the alkali metals are all very reactive. So if you take pure lithium and dump it in water, it will explode. Actually, it'll burn because they get more reactive as you go down. So cesium is the most reactive, and lithium is the least reactive. So as you go down, they become more reactive. The alkaline earth metals are fairly reactive, but less so than the alkali metals. So there we have beryllium, magnesium, calcium, strontium, barium. So they're just fairly reactive. The halogens, now moving to the other side of the periodic table. The fluorine, chlorine, bromine, iodine, and acetine are very reactive in their pure forms. And here I think is actually the opposite of the alkali metals, where the highest fluorine is the most reactive and acetine is the least reactive of the series. And so increasing reactivity. The noble gases are the chemically inert gases. Oops. So non-reactive. Alkali metals, very reactive. Halogens, very reactive. Noble gases don't react with anything. You have to really, really force them. So that's why helium is better for balloons than hydrogen, because hydrogen balloons can explode. Helium balloons will just pop. Okay, so to which group or family of elements does each element belong? Lithium. Alkali metals, yeah. Oops. Wait, is there L-A-I? It's just an I. Not great at spelling. Boron. Boron is a non-metal, which they don't really have a special name, but so I will do this too. Alkali is, those are alkali metals, but that's also 1A, group 1A. Boron is in group 3A. This is an I, not an L. For I? Iodine? Oh, you said halogen. Sorry, I heard which one for some reason. Halogen. So it's group 7A. And AR, argon. Noble gas. Yep, mostly just need to memorize those. Yes, ions. So as I mentioned, everything on the periodic table, neutral in its form on the periodic table. And we know that we can't gain or lose protons because that would change the element fundamentally. So the only thing we can do is gain or lose electrons. So if we have an element, let's use a concrete example here. Let's use lithium. So lithium, the periodic table is 3. So lithium has 3 protons. And in its neutral form, well, how many electrons does it have? So each proton has a positive charge. And it's neutral on the periodic table. So neutral lithium would have 3 electrons. So in its neutral form, every element has the same number of electrons as it does protons. So if we took one of those electrons away and we had lithium with 3 protons, because again, never going to change the number of protons, but just 2 electrons, what would the charge on lithium be then? We have 3 positive charges and 2 negative charges. So 3 minus 2, yeah, is a +1 charge. So lithium with 3 protons, 2 electrons would be a cation. So let me do this in red. Positive cations. So if we had lithium and we gave it an extra electron, 3 protons, 4 electrons, what would the charge be? Overall charge. It would be 3 positive charges, so +3, yeah, plus -4, -1. So lithium with 3 protons, 4 electrons would be an anion, and have a negative charge. So we write them like this, where the charge is in the top right corner. You can have things with more than a +1 charge. We usually write it with the magnitude of the charge first. So if we have calcium, we write it 2, then plus. Make sure that this is a superscript. So it's higher than calcium, right? It's a smaller letter at the top right-hand corner. Or if we had something that was negative, like oxygen, which usually forms a 2 minus charge. So, and then when there's just a +1 or -1, you just put a positive or minus. So in reactions, lithium atoms lose 1 electron to form lithium ions. So like I said in the previous slide. So lithium losing 1 electron means that it now has a +1 charge or 1+ charge. And the charge of the ion depends on how many electrons were gained or lost. So you take the number of protons minus the number of electrons, and that'll give you the ion charge. So for lithium ion, with 3 protons, 2 electrons, 3 minus 2 is 1+.
May I have your attention, please? This is Atlas IED.
Fluorine atoms will gain electrons. So we have fluorine, and we give it an electron from its neutral form. We get fluorine with a 1- charge. So again, the charge of the ion depends on how many electrons were gained or lost. So our ion charge is still the number of protons minus the number of electrons. So for F, fluorine ion, which always has 9 protons, and we gained 1 more electron. So in the neutral form of fluorine, it has 9 electrons. But when we give it 1 more, we have 10 electrons. So we get 9 minus 10 for a 1- charge. All right, so we have a nickel ion with 26 electrons. Got to go and find nickel. Nickel's here, has 28. This way. So nickel has 28 protons. It's just its atomic number. So 28 protons minus 26 electrons will give us a 2+ charge. So we have 2 more protons than we do electrons, 2+. And then bromine. Bromine is over here. So it's 35. Protons. And it has 36 electrons. So 35 minus 36 electrons equals a 1- charge. And phosphorus. Phosphorus is 15. This one.
May I have your attention, please? This is Atlas IED.
So 15 protons minus 18 electrons, 3- charge. Does that make sense?
May I have your attention, please? This is Atlas IED.
Should like keep tally and then send them as many emails as that thing goes off. May I have your attention, please? The PA keeps talking during my lectures. This is annoying. Yeah, so does this make sense? Yeah. Number of protons, number of electrons. Protons have positive charges, electrons have negative charges. So for sulfur 2-, how many protons and electrons does it have? the best way. I guess I could just slide over here. Okay, sulfur, element number 16. So because it's element number 16, that's its atomic number. 16 protons. Yep. 18 electrons. Because we have a -2 charge or 2- charge, we must have 2 more electrons than we do protons. Trying to decide if this is the best stopping point. Oh, let's get to isotopes. Yeah, let's just get to isotopes. Okay, so the number associated with the letter A above each main group column in the periodic table, 1 through 8, is the 1A, 2A, and then going over the right side is 3A, 4A, 5A, 6A, 7A, 8A, gives the number of valence electrons for the elements in that column. So valence electrons, get into this more in a later chapter, chapter 10. Atoms all have shells of electrons. So there are electrons that hang out sort of in the middle of their electron cloud. The valence electrons are the ones hanging out from the outside. So those outermost electrons, when one atom bumps into another atom, determines how they react together. So you can determine a lot of things about an atom based on those outermost electrons. So then main group elements tend to form ions that have the same number of valence electrons as the nearest noble gas. So this is why the group 1 forms +1 charges. If they lose 1 electron, so let's look at lithium. If it loses 1 electron, it'll have the same number of electrons as, this will be helium. Neon, argon. Then I think it's, let's check, krypton and then xenon. So they want to have the same number of electrons as a noble gas. So beryllium, which is 1, 2, 3, 4. So because this is element 4, has 4 protons, neutral beryllium will have 4 electrons, but it wants to have the same number of electrons as the nearest noble gas. And the nearest noble gas is helium, because they can go backwards. So if he loses 1, 2 electrons, then we'll have beryllium with 4 protons and 2 electrons. And he'll have a 2+ charge. On the other side of the periodic table, you have things like fluorine. So fluorine has 9, oops, didn't mean to do that. 9 protons. So it has 9 electrons when it's neutral, but it wants to have the same number of electrons as neon, the nearest noble gas. So it gains 1 more electron. So it has 9 protons, 10 electrons. So it has a 1- charge. Does that make sense? So you can use this for the element quiz 2 to help you determine what charge something should have by looking at the nearest noble gas. So this applies for these guys, which I think these 6 are on there. I think these 8 might be on the quiz. These guys are definitely on the quiz. So these are in 3A. So they can go back from here, right? This will be 1, 2, 3 jumps to get to B, or I guess 1, 2, and then 3 jumps to be neon. Whereas going to the right would be 1, 2, 3, 4, 5 jumps. So that's why they lose 3 electrons, gaining a positive charge, rather than gaining 5 electrons to have a negative charge. This is the nearest noble gas. Okay. Oh, Well, this is hard to do because there's not a periodic table in here. So we go back to this, and potassium has a +1 charge because the nearest noble gas is argon. So they go back upper row, but then to the end of the row before. And then selenium. This is selenium. So the nearest one, the negative charge is a little bit easier because you don't have to go backwards around the periodic table. But if we go 1 electron, 2 more electrons, that's why it has a 2- charge. All right, so here we are. Just the very end of chapter 4 here, we left off. Did we skip this one? Oh, no, we talked about this. All right, so these are the rules that I was talking about for memorizing those charges, or a table at least that shows them. But we were talking about the structure of the atom. And so this last thing that we're going to cover about just sort of individual atoms in general is isotopes. So we talked about how every element has a unique number of protons. That never changes. But the number of neutrons can change. And those are called isotopes. So it's the same number of protons, but a different number of neutrons. And these all occur naturally at different rates or in different proportions. So for something like neon, and this is one of the ways that we write isotope symbols. So you have neon 21. Now neon 21, actually I should keep this periodic table up. So neon's over here. We know it has 10 protons. This atomic number is 10. Whoops. So then this neon 21, the 21 is indicating the number of protons and the number of neutrons. We'll cover that in a second. But we can see here that neon 21 has an abundance of just 0.27%. So less than 1% is neon 21. Roughly 10% is neon 22. And then the vast majority, 90% of all neon that's naturally occurring is neon 20. So the number actually on the periodic table that we get here, this neon 20.18, is the weighted average of all the different natural abundances. And that'll be the last thing that we cover for this section, how to calculate that. So they all have these naturally occurring isotope abundances. So we saw the one way to write isotope symbols. This is the other one. You can write it with the chemical symbol represented by X here. And then as a superscript to the top left, we'll have the mass number. So that's the number of protons and neutrons. And then to the bottom left, we'll have the atomic number, which is Z, which we covered last week. And that's just the number of protons. So with this amount of information, you can easily calculate how many neutrons there are. Because this is protons plus neutrons. This is just neutrons. So the difference between those two numbers, or sorry, this is just protons. So the difference between those two numbers must be the number of neutrons. So we use A as the mass number, not to be confused with the atomic number, easy as that may be. That's the sum of the protons and the number of neutrons. So A, number of protons, number of neutrons. So then the difference, right, difference meaning subtraction, the difference between the mass number and the atomic number, so mass number, atomic number, is the number of neutrons. True for any isotope. So the notation that we saw on the previous slide about the abundances of neon is written out like this. And that's just the chemical symbol or name, right? So it could be neon Ne, or it could be neon spelt out. And then the mass number, because neon always has an atomic number of 10. We go You could have that memorized, or you could go look it up on a periodic table. And then with that information, figure out the number of neutrons for each isotope. Okay, so for chlorine, we're gonna have a chlorine isotope with 18 neutrons. We want to know the atomic number. So the atomic number is Z, the mass number A, and the symbol for chlorine isotope with 18 neutrons. So what's the first thing that we should look up? We find chlorine on the periodic table, right? So chlorine is here. All right, so, and its atomic number is 17. So that means it has 17 protons. And we just learned that the atomic number, I think we covered this last week, the atomic number is the number of protons. So Z is 17 protons. Then A, from just a couple slides ago, A is the mass number. So that's the number of protons plus neutrons. So in this case, it's 35. Well, let me write it out like this. All right, so it's 18 neutrons plus our 17 protons, which we found from the periodic table, equals 35 for our mass number. So we can write this out 3 different ways. We say that we have chlorine, which is Cl, is a Cl35. We could write out chlorine, the whole name, with a dash 35. Or we could use the symbol, then put the mass number to the top left and the atomic number to the bottom left. Any questions? Some rules to remember. So for this potassium isotope, how many protons does this potassium isotope have? Yeah, so the number to the bottom left is the atomic number. So 19. 19 protons is our, well, the number of protons and the atomic number. Then how many neutrons? Yeah, so the mass number is that one at the top left. So mass number equals 39. Then we know that the mass number is the number of protons plus neutrons. All right, so this is 39 plus, all right, it's out, protons plus neutrons. So 39. And we can just plug these in as if they're variables in an equation. So 19 protons plus however many neutrons will equal 39. So 39 minus 19 would be 20 neutrons. All right. So the atomic mass, not the atomic number, the atomic mass of each element listed in the periodic table.
May I have your attention, please? This is ATLAS IED.
So the atomic mass of each element listed in the periodic table represents the average mass of the atoms that compose that element. So for chlorine, we did chlorine 35 earlier. Chlorine 35 actually represents 75% of all chlorine atoms. The other 24% are chlorine 37. So chlorine 37 has a mass of 36.97 AMU. We usually talk in whole numbers, because kind of round things to those whole numbers, right? Because this is very, very close to 37. But in actuality, it is just a little bit less. And that's just the way it is. So its atomic mass, then if we want to calculate that average, and it says average atomic mass, but it's the weighted average. So instead of just adding everything up and then dividing by the number of things to get a regular average, we take each of our masses, right? So this is the 34.97, 34.97, and we multiply it by its abundance, 75.77 in this case, as a proportion. So we've taken that percentage, divided by 100 first, and we do that for each of these. So this is the 36.97 being multiplied by the 24.23, but as a proportion, or not as a percentage. So if you were to multiply these together, and then add those two numbers together, you would get 35.45. So that's the atomic mass. Yeah, I think this is one I remember taking general chemistry and being confused by this equation. So hopefully giving it a little structure like this can help you remember how to do it. I could never remember which things multiplied together and which things added together. But
May
this is
I
Atlas
have your
IED.
attention, please? This is Atlas IED.
Just going to go through and unplug all the speakers. What's that thing? Anyways. Okay, so this is the fraction of the isotope, 1. So that's the percentage converted into a proportion. Could also be called a fraction. And we multiply it by the mass of isotope 1. And then the fraction for 2, the fraction for 3, for however many there are. For most things, there's at least 2 isotopes. For some things, there's 3. I think for some things, there's probably even 4 isotopes. So this ellipse here, the dot, 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 means do this for however many there are. If there's less than 3, then you only do it 2 times. If there's less than 2, then you only need to do it once, but then your abundance of that one isotope would be 100%. So I think aside from remembering which things to multiply, which things to add, the other thing that can trip you up and you'll get the wrong answer and just be off by a factor of 100 is converting these and making sure that these are decimals, that they're fractions, proportions, not percents. But we'll do an example. So for magnesium, it has 3 naturally occurring isotopes with these masses given here. And natural abundances given here. And in a question like this, the first mass goes with the first percentage, the second mass goes with the second percentage, paired up like that. I'll probably just give you a table and say calculate the atomic mass. A little more straightforward. So we can set this up though, like this previous slide. So we've been given percentages, we've been given masses. So I think first thing I'm going to do is I'm going to write these 78.99%, 10.00%, and 11.10%. And we want to convert these to the fractions, to proportions. So we'll divide each of these by 100. So we'll get 0.7899, 0.1000, and 0.1110. So by dividing by 100, we just move the decimal places over 2. Now that we have these, so this equals this, we can take each of those and multiply it by its corresponding atomic or not atomic mass. Well, with its mass, right? Its corresponding mass. So this will be 0.7899 times our first mass, 23.99. The second one will be multiplied by the second mass, 24.99. And then this last one will be 25.98. So 0.7899 times 23.99 give you 18.9497. And we're not going to round at this stage because we're not done with our calculation. The next one will be 0.1 times 24.99. So we'll get 2.4999. That one's exact. And then we'll get 0.111 times 25.98. And that'll be 2.88378. And then we just add those together. You'll notice too that even though these masses are all roughly the same, this is why it's called a weighted average. So you can see that the largest number comes from our largest percent, right? Because this is multiplied by the 78. So we get 18 here. And then these other masses, which represent less abundant isotopes, are multiplied by smaller numbers. So there's less of those affecting the overall atomic mass. So we just add all of these together. And our final answer here, I guess before accounting for sig figs, would be 24.33338. How many sig figs should we have here? It's a trickier question, I know. Huh? Yeah. So this is where you got to kind of work through it step by step. So we have, well, this step here doesn't change anything with the sig figs because we're just converting it. This step here, we're multiplying, so smallest number of decimal places. Then in this number that we calculate from this, or smallest number of sig figs, right? So they both have 4, would be 1, 2, 3, 4. So then for each of these, because they each have 4 sig figs at this multiplication step, they'll each have 4 sig figs, but because these ones are smaller, they do actually have more decimal places. Did I put an extra 9 on here? Yeah. Oh, I did. Thank you. So these do have 3 decimal places, and when we're adding or subtracting, it's the smallest number of decimal places. So the 18.9497 only has 2 significant decimal places. So our final answer will keep only 2 decimal places. So 24.33 AMU. Any questions on those? There will definitely be one of these on the exam. So this is a great candidate for a piece of your cheat sheet. No questions? Okay. That's it for chapter 4 then.